Hello, today we will continue with chapter 5. We will revisit the work energy theorem because today we are going to introduce the work done by weight. Okay, so far we worked in the case where the weight of the object is perpendicular to the surface. So the work done by the weight was 0. And when that is the case, like in this example, the work is perpendicular to the surface of motion. So the work done by weight is 0, and we get W net or is equal to delta kinetic energy. Okay. Now, today we are, and W net over here in all the exercises we solved so far was only the work done by external forces, like if there is F in this direction, friction in the other direction. All the exercises we solved so far, the work done by weight was 0. Now, what if the work done by weight was not 0? Like in this exercise. In this exercise, this lady is sliding from a height h until it reaches the surface of the water. Okay, so if we draw this lady and we draw a free body diagram, the forces acting on it, there is a weight perpendicular to the ground, normal perpendicular to the surface, friction perpendicular parallel to the surface in the opposite direction, and it's moving a distance delta x from this dot until this dot. Okay, and it's the height is from this point until this point. Okay. Now we draw the free body diagram and we choose the x-axis and the y-axis. X-axis is along the motion. The lady is moving downward, so the x-axis is downward. Y-axis is perpendicular to it. Now the object is going down a distance delta x. So the work done by weight is Wx, which is the x component of weight, times delta x. Now, let's calculate the x component of the weight. We will do it exactly as we used to do it in Newton's second law. First, we draw Wx and Wy. Okay, then look at this triangle. Okay, look at this triangle. We have this angle here is theta. Assume it is 30. So this angle here is 60. So this angle here in this small triangle is 30. So this is theta and this is theta. If I look at Wx, it's facing theta. So Wx is W sine theta because it is facing this theta over here. So it is mg sine theta. Now I go back to my equation. Work done by W is the x component of the W delta x. Instead of the x component of the W, I will put mg sine theta times delta x. Okay. Sine theta is, now look at this triangle where one side of it is delta x, the other side of it is h, and this angle here is theta. The opposite of theta is h, and the hypotenuse of the triangle is delta x. So sine theta is opposite, which is h, divided by the hypotenuse, which is delta x. So instead of sine theta, I'm gonna put h over delta x. Okay. So now I have work done by weight is mg h over delta x times delta x. Delta x will cancel delta x and I will be left with work done by weight equal mgh. What is mgh? It is gravitational potential energy initial. Okay, it is mgh, it's gravitational potential energy initial. There is nothing next to it that is minus gravitational potential energy final, which is 0 if we take this as our reference. So we get work done by weight is gravitational potential energy initial minus gravitational potential energy final, which is minus delta gravitational potential energy, because delta gravitational potential energy, gravitational potential energy is equal to gravitational potential energy final minus gravitational potential energy initial. But this is gravitational potential energy minus initial minus gravitational potential energy final. So it is minus delta gravitational potential energy. Okay. Now, similarly, if an object is going upward, similarly, in the same fashion, we can also show that the work done by weight is minus delta GP. So always now, here is the theorem. You are not responsible for the derivation of this. You are not responsible. But if you want, if there is something not clear, you can send me an email and I can explain it again. But from all this, I want you to remember that the work done by weight is minus delta gravitational potential energy. So when do we have work done by weight? So work done by weight exists only when there is change in height. Okay, that is, there will be delta GPE. If there is no change in height, for example, when the object is moving on a horizontal surface, there is no change in height. In this case, delta GPE will be 0 because there is no change in height. Delta GPE is 0. The H final and H initial is the same. And work done by weight in this particular case will be 0. Okay, so in this particular case, work done by weight will be 0. So whenever you see horizontal surface, work done by weight is 0. Whenever you see change in altitude, then work done by weight is minus delta GPE. Now, let's go back to our work energy theorem. What does it say? It says work W net is equal delta kinetic energy. Let's take this particular example now, and let's apply the formula. W net is equal kinetic energy final minus kinetic energy initial, right? What are the work, what forces remain here in W net? I have work done by friction plus work done by W, okay, plus work done by normal, let's put them in small letters, is equal kinetic energy final minus kinetic energy initial. Work done by friction, I keep it. What's work done by work? Now I know the formula. It's minus delta GPE, which is okay, minus delta GPE. Okay, work done by normal is 0 because the x component of the normal is 0. This is equal delta kinetic energy. So work done by friction will be equal delta kinetic energy plus delta GPE. That is work done by friction is equal to delta mechanical energy. Okay, so now we have this new formula. If there is change in altitude, okay, if there is change in altitude, work done by friction will be delta mechanical energy. Even if there is no change in altitude, this is also the case, okay? Work done by friction from now on is delta mechanical energy, or W net is delta kinetic energy. The last idea in this lesson is power. Power has to do with, okay, so I have a force, it's doing some work. How much work it's doing per some time, this is the power, okay? And we are very interested in this, like when we buy an electrical device, we care about, we know that it will do some amount of energy in a particular time. So this will be my power, okay? Whose unit is what? So power is how much energy divided by delta T, okay? So there are two ways to derive power. One way is instead of W, I will put F delta X. So I will have P equal F delta X per delta T, but delta X per delta T from the first lesson, from the first chapter, it is V. So power is F times V. So if they give me the force and they give me the speed and they ask me to calculate power, I just do power equal F times V, okay? Another way to do the calculation, if W is delta KE, I know it now, W net is delta KE. So instead of W, I will put delta KE. So power will be delta KE divided by delta T. But delta KE is half mv final square minus mv half mv initial square, or half m into v final square minus v initial square divided by delta t. So depending on the problem, let's see this exercise. Your 1,500 kilogram car, so mass of the car is equal to 1,500 kilogram. Okay, is behind a truck traveling at 27 meters per second. So the V of the truck is equal 27 meters per second. To pass the truck, you speed up to 34 meters per second. So V car final, speed up to this, is equal 34 meters per second, and delta T equal 6 seconds. What engine power is required to do this? So here, as you see, there is V initial and V final. So I use which formula? There is no F here. If there is no F in order to use F times V, but I have delta kinetic energy because I have V final and V initial. So I use power equal delta kinetic energy, which is kinetic energy final minus kinetic energy initial, all of it divided by delta T. So power is equal, kinetic energy final is half mv final square minus half mv initial square, all of it divided by delta T. And now I just put numbers, so power is equal to half m is 1,500 times V final square 34 square minus half m 1,500 times V initial square 27 square, all of it divided by delta T, which is 6. Okay, I do the calculation using a calculator and I will get the power is equal to 53375 watts. The unit of power is watt. Okay, let's do another exercise. So here is the solution. Let's do another exercise. An elevator weighing 2,500 Newton. So I have the force is equal to 2,500 Newton. The force in this case is W, the weight. It's moving at a constant speed. So V is equal 8 meters per second. It's a constant speed. It's not changing. How much power must the motor supply to do this? So there is no change here in kinetic energy. So in order to calculate the power, I will just say it is F times V average. So power is equal to F, which is 2,500 times 8. And this is 20. Power is equal 20,000 watts. Okay. Okay. Let's move forward. So this is the solution. Okay. Now, a ball of mass m equal 1 kilogram slides down a rough curved surface AB and then along a rough horizontal surface BC. So there is roughness everywhere. So there is friction everywhere. We cannot apply mechanical conservation or mechanical energy. So friction exists, implies mechanical energy is not conserved. In this case, we must use work energy theory, because here mechanical energy is not necessary. So we have the mass is 1 kilogram, and there is friction everywhere. The speeds VA, VB, and VB, and C, distance BC and H are all shown on the figure. So I have VA, VB, VC, I have the altitude H, and I have BC all on the figure. By taking the reference of gravitational potential energy at the ground level, so here is the reference. Okay, so here GPE is 0. Here GPE equal to 0. Okay, at the horizontal, calculate the mechanical energy at each point A and B and C. So let's start part A. Mechanical energy at A is equal to what? What do we have at point A? It has velocity, so it has kinetic energy, right? And it has altitude, so it has GPE. So this is equal half mVA square plus mgh. Now I just do the calculations. This is equal. So half m is 1 times 1 times VA is 10. 10 square is 100 plus m is 1 times 10 times h is 1. Okay, and this is equal how much? So 100 over 2 is 50 plus 10. This is 60 joules. This is mechanical energy at A. Mechanical energy at B. Mechanical energy at B. What do I have? It's now at the GPE equal to 0. So there is no GPE. There is only kinetic energy, which is half mVB square. This is equal half m is 1 times VB is 10 square is 100. So half times 100. So mechanical energy of B is equal to 50 joules. Okay, so this is mechanical energy of B equal 50. And this is mechanical energy of A equal 60. Okay. Now, mechanical energy at C. Mechanical energy at C, also there is only kinetic energy. So this is half mVC square, half mVC square, and this is equal half times m, which is 1, times VC is 6 square, so 36, implies mechanical energy of C is equal 36 over 2, that is 18 joules. Okay? Okay. Now, part B. Deduce the work done by friction on the ball along the path A, B. So we want to deduce the work done by friction. What is the formula? Work done by friction. Work done by friction is delta. This is work done by friction from where to where? From A to B. From A to B. So this is equal delta mechanical energy from A to B. So this is equal mechanical energy at B minus mechanical energy at A and this is equal mechanical energy at B is 50 minus mechanical energy at A is 60. So this is minus 10 joules. Okay, then along the path BC, so now work done by friction along the path BC, this is equal again delta mechanical energy from B to C. This is equal mechanical energy at C minus mechanical energy at B. This is equal to 18 minus 50 equal minus 32. Okay, so we are applying the formula. Work done by friction is delta mechanical energy. This is part B. We are done with it. Part C. Calculate the magnitude of the friction force between B and C. Okay, so we have the work done by friction, and they're asking us to calculate the friction force. So the work done by friction is equal to what? Between the points B and C, right? So work done by friction between B, C is equal, its definition, this is, let's do it here, part C. So we have calculated the work done by friction between B and C, right? It is, oh, sorry, I deleted the, okay, I deleted here. Let me do it quickly. Okay, so calculate the magnitude of the friction force between B and C. So we are going to use the work done by friction between B, C. By definition, the work done by any force, it is Fx delta x, and Fx for friction is minus F times delta x, which is the distance BC. Work done by friction BC is equal minus 32. So this is minus 32 is equal to minus F times delta x, which is BC, that is 6.4. So I will get friction is equal to 5 Newton. Okay, and then deduce the coefficient of kinetic friction along the horizontal path BC. Now this is here horizontal path. I will use F is equal mu times N, okay? And this is equal to mu times M times G, which is W actually. So this is equal mu times M times G. Why is it the case? Because if I look at the horizontal path BC, N is equal to W, because summation of forces along the y-axis is 0. So N is equal to W. Okay, so now I'm gonna substitute, instead of F, I would put 5. This is equal mu times M, which is 1, times G, which is 10. So I get mu is equal 5 over 10, which is equal 0.5. Okay, deduce. Now part D, finally, the last part. If it takes a ball a time interval of 0.8 seconds, so I have delta T equal 0.8 seconds to move from point B to point C. Calculate the average power dissipated by friction. So we want the power by friction. So we need to use the work done by friction from B to C. It is 32. It is minus 32. Okay. So the power will be this work divided by delta time, which is equal 32 divided by 0.8, and this will give me 4 watts. Okay. So that's it for today's lecture. And if you have any questions, just send me an email and we will be solving, and I will be answering them during the next live session. Okay. Have a good weekend.